and Collections Environment, and we welcome Jorge Garcia. He talked about modeling, monitoring and mitigation, investigating the impact of structure-borne vibration on canvas paintings. Jorge started his PhD studies at University of Oxford in 2021. He obtained his bachelor's degree in biochemistry from Universidad Complutense de Madrid in Spain, and conservation at Universidad Politécnica de Valencia, where he obtained his MFA in conservation and restoration of archaeological objects and sculptures. He has worked at the National Gallery of London and as objects conservator in the Science Museum of different projects, both as freelance and private companies. So you have 30 minutes.
Hello, my name is Jorge, and I'm here to introduce my project that is trying to solve a problem faced by all of the institutions and galleries in the world. That is how to model, monitor, and mitigate the vibrations affecting a canvas painting. My project is being funded by the Art and Humanities Research Council. Co-authors of this work is Lynn Harrison in the National Gallery of London, and Catherine Hickett in the National Gallery of London, and Manuelis Hatchett at Oxford University. I'm working alongside with the National Gallery of London. So I will give you a small context. There are many things that can produce vibrations in a wall, like visitors, building work, transport, but what is important for us is to see how these vibrations can affect every individual painting on the gallery. And that's quite difficult. First, because we don't have as many accelerometers as we need, and second, because we cannot just attach an accelerometer in an historical painting. So normally, the gallery in some rooms, they have an accelerometer in a high-level position. What I'm trying to do with this project is how to link the vibration measured by that accelerometer to the values of vibration in the frame of the canvas painting and try to link that to the values of velocity, acceleration, stress, strain inside of the canvas painting. So I'm going to focus on a structure-borne vibration, meaning those vibrations traveling through the structure, and also I'm going to focus on canvas painting. A canvas painting is a very complex structure that is formed by a stretcher, and then we attach a piece of fabric that experiences stretching, wetting, and restretching several times until it's tense enough for us to paint. Then we apply a layer of size, we call it, that normally is an animal glue, and we apply a ground layer. After this ground layer has been applied is when we can start applying the color. But we cannot forget the importance of the frame, because it's the frame, the one that is going to be in touch with the wall. So I'm going to model this multi-layer system as a plate, following the assumptions of Kirchhoff's plate theory, meaning basically that, for example, that the thickness of the plate is much smaller than the others of the dimensions, that there are no shear forces, and that the lines normal to the neutral plane remain normal during and after the deformation of the canvas. So if I also consider the stretching force that I apply to stretch the fabric, I get to that very scary equation, and after a lot of maths, I can conclude that in order to calculate the velocity, the stress, strain, inside of the canvas painting, I just need 3 inputs, 3 values of acceleration that can be input in any point of the canvas painting with known positions. Results. Before I move to the results, I want to focus on concepts that we've been talking during the whole day. One is the natural frequency. By natural frequency, I mean the inherent vibration rate of a system without any external force. And resonance, that it occurs when the external force that we apply has a frequency that can match the natural frequency of the system, and that produces a maximum vibration and amplification of the signal. The first thing I want to talk about is how important is that stretching force that we apply on the fabric. So I'm going to work with a real painting. This is our test painting number 2 that I love to call Mary, I don't know why. And I have assumed 3 values of stretching force for the canvas. The literature reports values from 150 newtons per meter to 500 newtons per meter if we use the pliers. But I have calculated the 6 first natural frequencies for 50, 200, and 400 newtons per meter. The first thing that we can see is that as soon as I increase the stretching force over the fabric, the value of the natural frequency increases, and that's risky, meaning that I need to stretch the fabric because I need to paint on it. But the more I stretch it, the more I push it towards the values of the frequency range of some power tools, like a driller, a grinder, and so on. So this is the first example. The first example, it was in a gallery space, real gallery space, and I was working with Mary. And there were building works going around, so we could not see exactly what was going on, but we could hear that the gallery was generally quiet, and sometimes we can hear some grinding noises, some drilling. So the dimensions of the paintings are there. I positioned the accelerometers in those 3 positions marked in red. And for my calculations, I assumed a stretching force of 200 newtons per meter. So the first thing that I can show you is what the 3 accelerometers registered. Accelerometer 0 in blue, accelerometer 1, the signal in green, and accelerometer 2 in red. And it looks like they are measuring exactly the same. But if we zoom in, we can see that although they follow the same pattern, they are not exactly the same. And this is it. This is the power spectral density plot, a very fashionable name, that basically shows how the power of this signal is spread across the different frequencies, meaning that imagine that we can break a signal or a song into the different notes that compose the song. So that will be what we will get. So this signal had a lot of frequency content in 124, 125 hertz. So in the first column, what I'm showing is the frequency content of the signal that I was recording. And on the second column, what I'm showing is of all the possible values of the natural frequencies, those ones very close to the frequency content of the signal. And yeah, I was just trying to see whether there was a match, because if there is a match, we are risking amplification of the signal. So we have 23 very close to 21, 42 very close to 42.5. Yeah, so I'm expecting amplification. In here, what I'm showing is what my model calculated as an acceleration in the central point of the canvas painting in pink, versus what the sensor 0 was reading, was registering at the real measurement. I'm just plotting one because otherwise it will be very confusing. So yes, I can see that the signal has been amplified. But how much? The amplification factor of the acceleration is 1.7. So we are starting from that starting signal that it has a high frequency content in 125 Hz, 124. But if I look at the frequency content of the calculated signal, it has a very high frequency content in 23 Hz. But what for the rest of people that normally we tend to use the values of velocities instead of acceleration? So that is the acceleration of the sensor 0. This is the velocity that is associated to that acceleration. And what I want to know is how does it reflect inside of my canvas painting? So again, what I'm plotting in here is the value of the velocity calculated inside of the canvas painting in the central point versus, in black, the velocity of the accelerometer in position 0. So again, I can see that the velocity has been amplified. So how much? 1.7, that's the factor of amplification. And this is the moment of truth. So I wanted to say, like, okay, I'm calculating things, but I want to know how close these things are to the real measurement that I can register with an accelerometer. So in order to do the comparison, I went to the frequency domain, that is easier to compare the signals. On top is the signal that I calculated with my model, and on the bottom is the signal that was measured by that accelerometer inside of the canvas painting. The painting was not damaged, don't you worry. So what I can see is that, okay, they look quite similar. The peaks are in the same position. So I was very happy considering that. I have not put the mass of the accelerometer in my model. I have some uncertainties, like I don't really know how much the canvas was stretched. I don't even know how much is the dampening. I don't even know some of the mechanical properties of the materials that were used. So considering that, I felt quite happy with the results. But also, and what is more important, is that I can also calculate the deflection inside of every single point of the canvas painting. And I can link that to stress. That is quite important for everything that we have said about fatigue. So what would have happened if instead of 200 newtons per meter, I had assumed that my stretching force on the canvas was 400 newtons per meter, much higher? So the input signal is the same. And what it changed now is the calculated natural frequencies. They are higher. So I want to see whether they are matching each other. Yeah, I have 42, 44, 65, 61, 92, 90. So yes, I'm expecting resonance. Again, I'm plotting the acceleration calculated in the central point of the canvas versus the acceleration recorded by the sensor 0. And I can see that the signal has been amplified. How much? Slightly less, 1 to 5. So I started with that signal on top in black, with a high frequency content in 124.25, and now I'm getting this signal with a very different frequency content to the previous, that is that one. Okay, so I can see that the same input signal can produce two different response signals, and it just depends on how much I decide to stretch that fabric. So let's move to another room. There was a different room in the gallery, a different wall, and this one is suffering from, you can feel the vibration of the underground passing underneath. I'm assuming for the calculations, again, 200 newtons per meter. Why? Because we were doing some testing in the lab, and when we were stretching, we were roughly stretching that amount. So I thought it was a very good value to try. The accelerometers are placed in the same position, and this is the signal recorded by accelerometer 0, by accelerometer 1, and accelerometer 2. And again, they look exactly the same. But if I zoom in, I can see the same pattern, but they are not exactly the same. So they are doing different things. The frequency content of this new signal is very high, in around 24 hertz. So for the building work, it was about 124, very high. Now for the underground, it's 23. So I want to know what will happen to my painting. Let's see. So the frequency content of the signal is in the first column, 17, 23, 26. And the calculated natural frequencies of my canvas painting is 21, 31. So 21 is very close to 23. So let's see what happens. So if I calculate the acceleration in the central point of the canvas with my model, I can see that the signal is amplified if we compare with the black signal that is recorded by accelerometer 0. But how many times? In this case, the signal has been amplified almost 14 times. So I'm starting with a signal with a high frequency content on 23, and the resultant signal, the calculated signal, has a lot of frequency content, most of it in 23 hertz. So, as conclusions, I can say that my model is able to calculate this acceleration, velocity, and deflection, and the stresses in every single point of the canvas painting. I have some problems that I'm unable to find some important mechanical properties of the artist's material, like the Young modulus of the oil painting, or the linum, or the gesso, or there's a lot of uncertainties. Also, another important conclusion is that the force applied to stretch my fabric has a huge impact on the calculated natural frequencies, and that the same input signal can produce different response signals depending on the stretching force that I apply to the canvas. I have some things there, because, yeah. Actually, I'm also working in linking these values with the fatigue life. I'm also, as I cannot find these values, I'm checking similar materials, or materials that I think they may behave the same. I'm working in the model of the wall because that will allow me to move from the values of that accelerometer to the values of acceleration in the canvas painting. So I'm checking values to see how good they are. And also I'm modeling the behavior of the frame. So when everything is concluded, I will be able to link everything and go from that value of acceleration in the wall to the stress in the canvas painting. Thank you very much.
Thank you very much. So now we welcome, Eva Hartlieb. You speak now about vibration analysis in museums for paintings and the causes of vibration, due to the mechanical loads. So Eva Hartlieb is a conservator of paintings and painting sculptures. She completed her studies at the State Academy of Fine Art Stuttgart in 2021. Since then, she has been researching the damage behavior of paintings on canvas through dynamic processes at the Institute of Engineering and Computational Mechanics at the University of Stuttgart. So you have 20 minutes. Thank you.
Thank you. I think that's enough time. So I'm Eva Hartlieb. Thank you all that you're here. I am going to present you in the next minutes something I'm doing in my research since 3 years, and I wanted to emphasize that I'm actually a conservator for paintings and now trying my best in the field of engineering. And I'm going to talk about two topics, actually, but they merge together, of course. I'm going to present you about some measurements I did in museums, and also how those, I'm trying to do some basic research on how those vibrations are affecting paintings itself and how damage is occurring out of that. So, yeah. We had a lot of talks today about where vibration is, so I don't think I have to say that vibration, we can find vibration everywhere, from art transportation to construction site outside the museum, and of course also inside the museum, where the simple movement of a visitor is already exciting the painting surface. And yeah, vibrations are mechanical processes which cause visible damage and also microscopic alteration due to their commutative behavior, and also, of course, because of single events. In my research, I'm trying to understand where are those excitation sources and how high are they, but I also want to understand how damage is developing on paintings. So, to give you a short outline, what I'm going to talk about, I'm going to talk about some measurements I did in 2 different museums, where I measured 3 different scenarios, what kind of measurement equipment I used, and how I analyzed the mass of data. I think it was 500 hours of data I got out of that. And then the second part, this is the part I'm currently working on, is how actually is damage developing on samples, where I am doing experimental research in the lab of the ITM, the institute I'm working at. So the 3 scenarios I would like to talk about in detail. I'm only going to focus on one of those. But you can see there are 3 different buildings, 3 different problems, 3 different questions, like what is coming from the outside of the traffic in front of the museum, what is coming from like a Christmas party, which is happening above a museum, above the exhibition room, and also what is really happening when there is a really hard music event under exhibition room. So the measurement equipment I used in all of those museums are mainly the same. I used acceleration sensors, which were located at different locations at like the wall or the floor, and if possible, and once it was possible, to attach a 1D sensor on the back of a painting. And also a laser Doppler vibrometer helped out to measure the dynamics of the painting surface. The signals I got, I told you it were over 500 hours of signals. I looked at them on the time domain, where I could find like special events, what is happening, especially on a painting surface when, for example, a visitor enters the room. So I would like to understand specific situations. But also the rainflow counting method occurred to be a very good technique or method to analyze all this data, and also to give somehow, or to make it possible to compare all those different scenarios which is with each other. This rainflow counting method is originally developed for fatigue analysis, and it is a cycle counting technique which defines the signal in specific amplitudes and counts those cycles accordingly. So to say it shortly, this method reduces the data into relevant cycles and its amplitudes. Where I'm getting out those tables with a lot of numbers. So I want to talk about one of those scenarios, because, as I said, it would take too much time, where there was happening this music event in one of those museums. And when we look into the signals, I compared the acceleration or the excitation levels on what is happening when there is nothing going on, or when there is like just a normal visiting day, and what is happening when there is this music event. And in this plot, you can clearly see the songs played after one another. And so there's, of course, as you can see, an increase of excitation during this music event. And when we now look into what the rainfall counting method is giving us, we can see that during the music event, there is a shift of higher excited amplitudes, and also those were more evenly distributed over those ranges. So, but what to do with all those measurements and all those data? So here you can see some numbers of those three scenarios, where you can see, depending on the situation, depending on the excitation source, different kind of amplitude levels are excited. But to maybe give you or help you to understand what those numbers mean, I'm showing you here some excitation amplitudes, some amplitudes which were excited during an art transportation, so they're much higher. Yeah, so what to do with all those numbers? So what now? So what we could see, or what could I see during those measurements, that of course vibration levels are dependent on many parameters, as we already heard in a lot of talks today. And this is also the problem, that there are too many parameters, and I, for myself, found out that it's helpful to compare compare situations with a baseline. Like, for example, I showed you compare what is happening when there is what kind of excitation levels are coming up during normal visiting hours, and when there is, for example, this music event, to see okay, what higher levels are excited. So what now? I could do more measurements in museum to fill like a database, to get more information out of all those data, but it would take me more time, because doing measurements is very time consuming, and mostly the analysis of that. And for me, it's like, is this information really more valuable? I think there are more interesting questions to ask, like what is really going on with the artwork itself, and how much can it withstand? And I think these questions were already asked by Bill Way at the beginning, so it's very nice that he already asked this question. And yeah, so how much is too much? This depends, of course, on the excitation levels, but also, of course, of the materiality of the paintings itself, like how old are they, what are they made of, how is it layered, how is it constructed, the dimensions, and of course the history of vibration, like, okay, where are there some pre-damages? And in my research, I'm trying to reduce the scope of an investigation to understand the basics first, so fundamental research. Fundamental research I'm trying to do with, I'm working with samples I'm doing where I'm defining the material compositions, because as we all know, paintings are very complex. And yeah, on those samples, I'm doing fatigue tests on. Those fatigue tests, I'm putting cyclic load on them to see when crack or when failure is occurring. And with this experiments, I'm trying to then generate SN curves. So I'm happy that Bill Way today in the morning explained how those SN curves work, so I don't need to do that now. Yeah, the samples I'm working with, they are made with, in cooperation with the State Academy of Fine Arts in Stuttgart. And basically, they have a canvas or made out of linen, a primer, and a paint layer. The paint layers, right now, we decided to work with aged oil, artificially aged oil samples, and acrylic, because, yeah, to have like a more broader materials. And the geometry of those samples, they're like only 7 centimeters high right now, but they can always change. They have a predefined breaking point to already specify the area of damage. These samples are then put on the newly developed test rig on which we are doing those long-term fatigue tests. And easily said, we are putting those samples on a shaker, and the shaker is then excited with defined amplitude and frequency. And yeah, so I'm shaking them until they break. But of course, it's not always that easy. There is a very complicated system behind it. This test rig is performed by DSpace and the model to control this shaker, and also the specimen, the sample is then modeled with Simulink, and it's a software from MATLAB. And yeah, in this test rig, I'm trying to control, or no, I'm not trying, I'm controlling the excited frequency, because I want the sample to shake in its first bending eigenmode. And I'm also controlling the amplitude in which it is shake to generate those SN curves. Of course, it's always important to also control the humidity, because in preliminary tests we found out that the dynamic behavior is, of course, changing with the humidity. So, sorry. I wrote a paper on this test rig. That's why I'm not going into detail on every of those instruments, but afterwards you can ask me, of course, a lot of questions if you want. And to show you some preliminary results, on the left you can see a plot where the amplitude and the frequency were like controlled in an open loop system, meaning there was a constant energy input and a constant frequency. And over time, or over cycles, of course, we're talking always in cycles, something changed already in the sample. With the high-speed camera, which is documenting this damage development, we couldn't see any cracks, so there must be like material fatigue already starting on a microscopic level. And this also means that there's a change in the dynamic behavior, meaning there's a shift of the first eigenfrequencies. So to get to the plot on the right, which I want to generate those SN curves, because I want to have a constant amplitude over the time, this test rig needed to be designed in a closed loop control system. Yeah, and to give you some idea on how this damage is developing on those samples we created, you can see that after a longer time of stress on those samples, first damages are occurring in the edges of the predefined area, and after some time the crack merged into the entire width of the sample. Yeah. At this point, I am doing a lot of tests, but I am not ready to show you some SN curves because we are still in the making of them. But so coming to this conclusion, I want to say some short words to the first part where I did some measurements at the museum. I wanted to say that this measurement equipment enabled me to do a precise mapping of how vibration is transferred from outside into the building and also into the painting. And the data showed that it is important to evaluate those measurements individually, but the rainfall counting method is like giving me a possibility to somehow compare all those vibration levels with each other. In the second part, where I'm now starting all those experiments in the lab, I can see and I can say that vibration is causing damage to those samples, and it is changing the dynamic behavior of the samples. And the test rig is enabling me to do those long-term fatigue tests on. And the test rig is in need of this closed loop control because, as I said, we need to have a constant amplitude and also a frequency controller, which is shifting the starting frequency to the frequency I need it to. And yeah, the last slide I showed you is that damage is developing in different steps. And in my case, I am focusing on the damage crack. Oh. And yeah, so coming to an end, what am I going to do in the future is I'm going to do more of those experiments to maybe try to do those statistics Bill Wade talked about, to generate those material-specific SN curves, and yeah, find answers to how much is too much for a painting. And yeah, so thank you very much for your attention. And
so keep your question for the end of session. Alors je passe au français parce qu'ils sont majoritaires dans les présentations de posters. Donc peut-être si vous pouvez arriver ensemble, 1, 2, 3, 4, 5. Donc Hélène Boudin et Hélène Huisson. Ouais, je vais vous représenter au fur et à mesure. Donc il y a Amandine Hélène, Aimé Claire Guérin et Marina Biron. Donc je crois que l'exercice est toujours 5 minutes à chaque présentation. Donc on commence avec Hélène Boudin et Hélène Huisson, hein, c'est ça, du musée d'archéologie nationale, domaine de Saint-Germain-en-Laye, en France.
Alors, bonjour à tous. Nous allons vous présenter ici des données qui ne sont pas chiffrées, mais on est dans le concret, on est dans le réel. C'est les preuves et les indices des conséquences des vibrations directes sur les œuvres, identifiées grâce au constat d'état que nous avons pu réaliser avec l'aide d'équipes de restaurateurs dans le cadre de chantiers de collection, en particulier celui de des collections de la Gaule romaine et sur les journées d'entretien des collections, sur les œuvres exposées dans les salles ouvertes au public. Voilà, la preuve en image, les objets sont là, en place, on a des petits plots, et les vibrations provoquent, dans le cadre de travaux, de déplacements, de passage du public, d'ouverture des vitrines. On a des vitrines anciennes dont le mode d'ouverture très mécanique fait bouger des objets et qui provoque en fait des chutes d'objets, des déplacements de plots qui, dans le cadre des travaux, sont récurrents, peuvent survenir toutes les semaines et dans un cadre fonctionnement normal, hors travaux, sont beaucoup plus réduits, entre 4 et 6 mois. Voilà. Pour vous donner quelques chiffres, voilà, ils sont tirés des journées d'entretien des collections. On a pu réaliser sur 4 ans 3588 constats sur les œuvres exposées dans nos salles du néolithique, de l'âge du bronze et du premier Moyen-Âge. Et on voit que les accidents liés aux vibrations sont assez réduits. On a eu 16 problèmes, 16 chutes, qui nous a obligés à revoir 77 soclages. Il nous reste encore une petite série à traiter. Globalement, on n'a pas de problèmes structuraux sur ces accidents liés aux vibrations. Mais voilà, Hélène va mieux en parler que moi. Là, vous voyez en fait quelques images des soclages trop serrés, des soclages révisés, des soclages aménagés pour permettre aux objets, 1, de rester en place et 2, de ne pas subir de dégâts liés à ces socles trop serrés, griffures, rayures, voilà, altération. Corrosion des métaux.
Concernant les altérations observées qui sont amplifiées par les vibrations, sont essentiellement concernées les altérations mécaniques évidemment. Et en fait les facteurs intrinsèques d'altération spécifiques aux matériaux constitutifs des collections sont donc démultipliés par les vibrations. Donc les cassures et fissures sont très essentiellement liées à d'anciennes restaurations. On remarque des chutes de fragments ou de la perte de matière avec la perte d'écailles. Il y a naturellement, dans le cas des métaux archéologiques, le processus de corrosion, mais la perte de matière est accentuée bien sûr par les vibrations. On note aussi des déplaquages et des desquamations, les frottements des soclages ou des dispositifs de suspension comme en haut à droite qui accentuent encore la perte de matière, et tous les systèmes de pattes qui induisent des rayures superficielles sur les objets, des fissures qui s'écartent au fur et à mesure en fonction de l'intensité des vibrations et de leur répétition.
Alors, suite à l'ouverture du musée dans les années 60, des systèmes de compensation ont été mis en place pour éviter que les objets ne bougent de trop. On est allé assez loin en fait dans ces mesures de compensation, et on voit ici par exemple une petite statuette de terre blanche pluguée sur son système de fixation qui sert directement à l'accrocher dans la simèse. C'est fixé avec du plâtre. Nos sculptures se sont vues rajouter également des bases en béton pour stabiliser en fait leur assise. On voit que tout ce qui est sculpture de métal ou de terre cuite ont amplement été goujonnées, percées avec des implants de tiges, goujons, on peut les appeler comme on veut, on a de tout. des vis, voilà, que ce soit des tout petits formats ou des formats plus lourds, comme le lapidaire. On est même allé jusqu'à coller les objets sur des tablettes en plexi. Voilà. On a retrouvé en fait 94 petites sculptures de terre cuite blanche de l'Allier collées sur les tablettes. Donc là, on est sur des sols en parquet qui bougent, avec des vitrines qui bougent à l'ouverture et voilà, une stabilisation mécanique forte.
Et donc au musée, on a actuellement des gros projets de réaménagement avec la destruction et la reconstruction d'un escalier dans l'angle sud-ouest. Et on voit ici que ça va potentiellement avoir un impact sur la restauration en cours d'une grande toile marouflée dans l'ancienne salle d'archéologie comparée, enfin salle de Mars. Et on peut se demander ici justement dans quelle mesure les fissures déjà présentes pourront être aggravées et pourront avoir une incidence sur l'œuvre. Et là, c'est un petit appel à Sandy, si jamais vous êtes intéressé, pour nous aider à étudier, à mesurer la possible évolution de cette fissure structurelle dans le mur mitoyen de l'escalier, dont les travaux ont lieu en même temps que la restauration de l'œuvre, malheureusement. Merci.
Donc nous accueillons maintenant Amandine Hélène, conservatrice restauratrice indépendante en France.
Alors, dans ce sujet des vibrations dans l'environnement des collections, je voulais réfléchir aux objets horlogers en fonctionnement et le risque des vibrations pouvant provenir de l'objet lui-même. Et donc, puisqu'il s'agit plutôt de pistes de recherche, mes problématiques vont être plutôt présentées à la fin de cette présentation. Et je vais vous montrer deux exemples d'objets horlogers et automates en fonctionnement, avec des choix de fonctionnement différents, puisque le premier est en fonctionnement permanent et le second fonctionnement occasionnel. Donc, la typologie des objets horlogers comprend donc des objets d'affichage et mesure du temps de diverses tailles, donc des montres de poche qui sont rarement maintenues en mouvement dans le cadre muséal, jusqu'au patrimoine monumental comme les horloges d'édifices, souvent maintenues en mouvement puisqu'elles font généralement partie de monuments historiques qui sont toujours en utilisation. Cela comprend aussi des automates, donc des objets possédant un mécanisme horloger central, mais qui est combiné avec de nombreux éléments mobiles et des mouvements complexes, des figurations humaines ou animales, comme vous voyez ici, qui effectuent des actions spécifiques. Donc, ce sont aussi des objets qui possèdent régulièrement des éléments sonores comme des cloches ou des sonneries musicales. Donc, le mouvement est intrinsèque à ce type d'objet, ce qui peut poser une contradiction par rapport à un objet muséal ou patrimonial que l'on cherche à maintenir dans un état stable en limitant les interactions avec son environnement. Cependant, le mouvement fait également partie de l'existence même de l'objet et de sa compréhension, et donc son arrêt implique une perte d'information et de sens. Donc la remise ou le maintien en fonctionnement est central à la conservation, la restauration et l'exposition des objets horlogers, qui demandent d'évaluer les conséquences et les pertes qu'impliquerait un fonctionnement comme un arrêt de l'objet. Si les restaurateurs intervenant sur ce type d'objet ont déjà l'habitude de prendre en compte les risques liés à l'usure, à la friction et aux forces directes dans leur prise de décision, l'étude des vibrations et leurs conséquences sur l'ensemble de l'objet peut être un critère intéressant de cette réflexion et permettre d'aider à la prise de décision et éventuellement la mise en place d'un protocole d'entretien ou de contrôle en cas de fonctionnement. Petit bug. Une seconde. Donc, un mécanisme horloger utilise de l'énergie cinétique avec un apport extérieur qui est d'abord stocké dans un organe moteur, ce que vous voyez en rouge, qui est ensuite transféré par un organe de transmission avec suffisamment de force pour contrer la résistance liée au poids des éléments et passer de l'inertie au mouvement. Cette énergie rejoint ensuite un organe distributeur qui transforme l'énergie cinétique reçue en mouvement des éléments extérieurs. Si les organes de transmission et de distribution ont pour objectif de cibler le chemin que prend l'énergie, une partie peut être perdue dans le reste de l'objet sous forme de vibration. Si le mécanisme est correctement réglé et huilé, en revanche, la perte peut être minimale. Les horloges et automates peuvent être composés d'une variété importante de matériaux, avant tout des métaux pour les mécanismes internes, mais également pour la structure externe, des métaux ou du cartonnage. Et pour les décors et éléments extérieurs, on peut avoir du verre, de l'émail, également des textiles et des papiers pour les automates plutôt du XIXe siècle, et bien sûr des couches picturales qui sont assez variées. Certains de ces éléments sont eux-mêmes en mouvement, comme les organes d'affichage, les aiguilles d'une horloge par exemple, ou les parties mobiles d'un automate, voire comme celui-ci, l'automate entier. Si les métaux sont probablement les matériaux les moins sensibles aux vibrations, ils peuvent, au terme de mouvements, forces, vibrations répétées, ils peuvent développer des fissures, voire des cassures à cause de la fatigue mécanique. Ils ont également des propriétés conductrices, entre autres des sons et des vibrations, ce qui peut être un inconvénient pour les autres matériaux de cette typologie d'objets puisqu'ils sont en contact direct. Donc, au terme de ce colloque, et si j'ai la possibilité de poursuivre cette recherche, donc il y a 3 pistes de réflexion que j'aimerais pouvoir développer afin de comprendre l'impact des vibrations dans la conservation d'un objet horloger et utiliser l'étude acoustique pour déterminer la viabilité d'une remise en fonctionnement. Donc, comment mesurer les vibrations endogènes produites par le mouvement dans l'objet même? Peut-on connaître l'intensité des vibrations présentant un risque pour les différents éléments et matériaux de l'objet? Et par quels moyens peut-on diminuer les vibrations depuis l'intérieur de l'objet, par exemple par la mise en place de matériaux ou d'éléments tampons, ou par le réglage et l'entretien du mécanisme? Merci.
Nous accueillons maintenant Aimée Sims, de Heritage, qui est restauratrice du patrimoine et des collections du palais de Westminster, House of Commons de Londres.
Hi, thank you for having me. So, the Palace of Westminster, otherwise known as the Houses of Parliament, is unique in being continuously used as the seat of national government for the United Kingdom for nearly 1,000 years. Developed from its origins as a monastic foundation into a royal palace, it's now a global symbol of parliamentary democracy. Following a fire in 1834 that destroyed large portions of the medieval buildings, architects A.W.N. Pugin and Charles Barry were commissioned to rebuild the palace in the Gothic revival style it's famed for today. The palace is a Grade 1 listed building and alongside Westminster Abbey forms part of a designated UNESCO World Heritage Site. The palace has not undergone extensive renovation for around 70 years and is expensive to maintain, requiring a comprehensive set of works to address aging building fabrics and systems. In 2019, the Restoration and Renewal Programme was established to undertake the extensive and essential work needed for the palace to remain the working home for UK Parliament and ensure its preservation for future generations. Conservation of both the architectural fabric and Parliament's unique and diverse heritage collections was a key consideration. Parliament's heritage collections are made up of significant historical and contemporary artefacts which are integral to the palace and the history of the site. They are the material culture of Parliament, part of the democratic process, both ceremonial and in daily use. As such, they form a fundamental part of the palace's heritage, not just of the building's significance, but of its identity. Due to the complex and extensive nature of the building restoration work needing to be undertaken, the Delivery Authority, as part of the R&R programme, will be responsible for the decant of the collections from the building for the duration of the works. These will include the Parliamentary Art Collection, the Historic Furniture and Decorative Arts Collection, and the architectural fabric collection, a total of about 12,000 items. However, there are some items that will be remaining in situ and will be protected throughout the construction alongside the historic building fabric. The construction work that the palace will undergo is expected to be physically intrusive, with new lifts being introduced for fire evacuation safety and improved accessibility, as well as potential tunnelling works under the building for new services to be run. It's predicted these works are likely to have a high vibrational impact on the in-situ heritage collections and the historic building fabric. We've been undertaking a period of extensive pre-construction survey work across the palace, and an important strand of this is the building vibration survey. Parts of the accession collections cannot be removed because they are quite literally built into the building, either as wall paintings, mosaics, sculptures, or in a few cases, because of the logistical difficulties and the associated risks posed by attempting to remove them. This work is some of the most complex that the conservation team is undertaking, simply because of the scale of the building itself, the variety of the media affected, and the specialist nature of the work. A small but detailed study on the impact of construction-generated vibrations has previously been undertaken at the Palace of Westminster. From October 2016 to March 2017, the Parliamentary Heritage Team undertook a programme of vibration monitoring due to masonry restoration in a part of the palace called Chancellor's Court. Stained glass windows are situated directly above two large wall paintings by Daniel Maclise, which are exceptionally vulnerable to vibration due to the water glass technique with which they've been applied to the walls. Additionally, cracks were observed running through the already fragile plasterwork, and these were stabilised and then closely examined during the masonry restoration in case there was additional movement. While this monitoring is an example of best practice, the template cannot be directly transferred to the wider programme across the palace because of the type and quantity of equipment needed, as well as the increased specialist scope of the survey. Thus, we have developed and are about to undertake a completely new palace-wide vibration survey. The building vibration survey is currently anticipated to occur in 3 stages: defining our metrics, so an initial year-long programme of monitoring to establish baseline vibration characteristics across the palace, important to identify existing tolerances and acceptable thresholds. Data collection for this stage is about to commence January to March 2025. Testing. Secondly, a period of testing using exemplar construction techniques to induce vibrations and examine the impact these actions have on the existing vibration levels, alongside a direct examination of the heritage. This will allow a further development of threshold limits and preferred construction techniques that, if kept to, will substantially reduce the risk to the heritage. Construction. Finally, long-term monitoring across the palace during the construction phase of the R&R programme. Construction techniques can then be adapted or modified as required to minimise the risk to heritage. The biggest challenge we anticipate is how to measure and assess damage. Currently, we are focused on setting realistic threshold limits, but do not have a detailed post-alert condition assessing and damage response plan created. Next summer, there will be several boreholes dug into the foundations of the building, which will be the first time on our programme that any intrusive surveys have had the potential to cause significant vibrational impact. It's imperative that we have a comprehensive plan ready to support this work. Thank you to the Institut National du Patrimoine for allowing me to present today, and I look forward to discussing our challenges in the workshop tomorrow.
Et donc, vous êtes, Claire Guérin ou...
Oui, moi je suis Claire Guérin. En fait, Marina, elle n'a pas pu venir, donc du coup, je suis toute seule.
D'accord, très bien. Donc Claire Guérin, conservatrice, restauratrice indépendante en France.
Oui.
Merci.
Alors, je ne sais pas, j'ai appuyé dessus, mais il n'a pas l'air de...
Il faut attendre un peu. Voilà,
d'accord.
Que ça...
Ah bah, ça tombe bien. Alors voilà, ce qui se passe, c'est que j'aurais dû présenter un poster. Et enfin, on aurait dû présenter un poster. Et en fait, ce matin, j'ai eu un petit problème technique, donc je n'ai pas pu l'installer. Donc voilà, donc il n'y aura pas de poster. Je suis désolée parce que en fait, c'était tout est là, puisque c'est une solution que nous avions trouvée avec une autre restauratrice qui s'appelle Laura Resina pour les vitrines anti-vibratoires et des mises à distance anti-vibratoires qui fonctionnent depuis certaines depuis 2010, donc c'est dommage. Donc là, je vais vous lire un petit texte très vite et je vous présenterai certaines vidéos qui nous ont donné envie finalement de travailler sur ces vitrines et sur ces mises à distance et sur autre chose, mais on n'a pas pu le présenter. Donc voilà, ce poster présentait diverses solutions empiriques visant à maîtriser les vibrations susceptibles d'affecter les objets présentés en vitrine. Il faut garder en tête que les objets de musée sont toujours en mouvement, même au repos. Ils sont soumis à une succession de vibrations ponctuelles ou constantes, de différentes intensités parfois peu perceptibles. Or, ce cumul d'agitation associé aux enchaînements des variations thermohygrométriques entraîne sans conteste une fatigue des matériaux constitutifs des œuvres. Les paramètres de la conservation en sont modifiés. La connaissance de l'état des œuvres, de leur historique de mouvement, des propriétés des matériaux, des spécificités des divers équipements, des caractéristiques des bâtiments et la perception du comportement des publics est précieuse. Mobiliser nos sens, regarder, écouter, toucher, discerner, analyser les graphiques des enregistreurs de données nous permet d'identifier ces risques et de les évaluer. C'est ensuite au niveau de la source de transmission des vibrations que nous agissons, quand c'est réalisable, pour réduire réellement l'émission des vibrations transmises aux œuvres. La contribution des professionnels, transporteurs, manipulateurs, scénographes, commissaires d'exposition, régisseurs, menuisiers, socleurs, conservateurs-restaurateurs, agents de surveillance, agents de maintenance, etc., nous aide à concevoir une stratigraphie d'habillage adaptée aux spécificités des œuvres qui s'inscrit depuis le transport jusqu'à leur présentation. L'objectif étant d'agir au mieux dans l'intérêt de l'objet, du musée et du public avec les moyens de contrôle à disposition. La stratigraphie d'habillage des vitrines est réfléchie à partir du bâtiment et de ses spécificités architecturales, de ses équipements, de son public, de ses collections, etc. La réduction des vibrations est requise notamment dans le cas de parquets flottants, de structures élastiques, de réseaux de transport souterrains, de conditions thermohygrométriques à risque. À ceci peuvent s'ajouter l'affluence du public, férus de selfies ou de performances postées sur les réseaux sociaux, la localisation des vitrines en salle, les espaces de circulation réduits, etc. Une réflexion collégiale est donc essentielle. Aujourd'hui, la politique de développement durable nous en donne les moyens. En effet, il est désormais possible de réaliser des vitrines et d'investir dans des mobiliers et des matériaux plus performants. Les expérimentations qui peuvent alors être effectuées dans les situations dissemblables permettent de rendre les vitrines polyvalentes, avec toujours pour objectif d'améliorer la protection des œuvres. D'autres outils anti-vibratoires, comme les mises à distance, ont la capacité de faire face à un manque d'infrastructures ou d'équipements afin de répondre aux impératifs des conservations des œuvres, à condition toutefois de s'adapter à la scénographie, à l'éclairage, au parcours et à l'affluence du public. Elles ont l'avantage de pouvoir habiller des vitrines standards, le vide devient notre ami. La taille des caractères des cartels et leur positionnement s'avèrent être un atout important pour la réussite de la protection. Inversement, elles demeurent insuffisantes parfois et nécessitent le rajout de pictogrammes de mise en vigilance pour que tous les publics interagissent naturellement avec les prescriptions de préservation des œuvres. L'implication de tous les facteurs esthétiques, budgétaires, sécuritaires, conservatoires, etc. et de tous les acteurs est primordiale pour trouver des solutions viables, acceptables et satisfaisantes. Alors, je vais vous présenter des petites vidéos. Donc ça, c'est les tests préalables qu'on fait sur des vitrines quand on veut... Quand on a un objet, alors évidemment, en général, on utilise le même poids, par exemple la bouteille, parfois la même hauteur, mais enfin, parfois, c'est juste pour voir ce que vous voyez là, donc c'est-à-dire pour vérifier que l'impact est important ou n'est pas trop important, c'est-à-dire viable. Alors ça, c'est l'importance d'une réflexion collégiale, c'est-à-dire quand on arrive et quand on installe des expositions, voilà, on se retrouve avec des vitrines, mais elles sont déjà faites, tout a été fait, et en fait, la mise à distance n'a pas été comprise. Donc, évidemment, on a des problèmes, d'où l'intérêt d'avoir une réflexion collégiale en amont, c'est-à-dire de ne pas avoir des vitrines qui sont trop longues et pas assez larges, d'être lestées, etc., etc. Enfin, tout le monde en a vu. Ça, pareil, c'est les tests de vibration. Parfois, on a des portes dans les musées, portes coulissantes ou portes normales. Et au final... Ah, c'est dommage, on n'entend pas le bruit. Ah, c'est dommage. Bon, je ne sais pas si là, Voilà, vous voyez, vous entendez le bruit. Donc là, en fait, on mobilise les gens pour que tout ce qui est ce système de porte puisse être utilisé d'une façon je ne sais pas comment dire, mais il faut que les personnes qui travaillent dans le musée soient convaincues de l'importance de manipuler les portes d'une certaine façon. Une approche de vitrine délicate, donc ça c'est les structures élastiques avec les supports. Donc ça en fait on ne touche pas la vitrine mais on s'approche. Donc ça c'est la même chose. Et donc là, le projet qu'on présentait dans le poster, c'était ça, c'était pour montrer qu'on avait des objets qui bougeaient normalement comme ça, avec un support, une structure élastique. Et grâce à cette vitrine, on arrive justement à pu avoir ce mouvement. Pas avec ces œuvres-là, puisque ce n'étaient pas les œuvres du musée, mais d'autres. Ça, c'est l'incidence des travaux de voirie. Donc j'ai mis que c'était réalisé avec une œuvre factice. Donc vous voyez la partie... Et ça peut durer des mois. Parfois même 1 an, 2 ans, et puis si vous avez toutes les œuvres comme ça, ben voilà, pendant 1 an ou 2 ans, c'est assez régulier, vous avez ce genre de vibration. Et là, c'est le choix du camion. C'est un camion avec une suspension pneumatique, mais là, on ne parle pas de suspension pneumatique, on parle de la vibration sur la caisse du camion, qui bien sûr se répercute directement sur votre caisse. Voilà, c'est tout, j'ai fini.
Si, c'est pas grave. Donc on termine avec un peu d'avance la séance des questions et puis de discussion. Est-ce qu'il y a déjà une question pour un des intervenants, un ou une intervenante dans la salle? Sinon, j'ai une question pour ouvrir le bal. I have a question for Eva. Where is Eva? You mentioned that the humidity in air is changing. Oh, you can go there. Excuse me. Yes. Well, I forgot to say I'm Jorge. Also, thank you. So you mentioned that humidity can change the results of monitoring vibration for the same object in the same context, but you know how it changes? It's worse, it's better?
No, it's not worse or better, it's just changing the dynamic behavior, meaning if, so I made some tests with specimens, and I excited this specimens in a humidity chamber, which was calculated on 50%. And then I did the same measurement and only changed the humidity, and different kind of eigenfrequencies occurred. So I characterized the dynamic behavior by saying, okay, this and this and this are the eigenfrequencies of the painting, and changing the humidity is also changing the eigenfrequency. So talking about eigenfrequency in this case is like it changes depending on the humidity of the painting. So this is what I found out in my experiments. So it's not worse or better, it's just changing,
okay,
different.
Yes. Okay, yeah. Thank you very much.
I have two one question and one comment. I have first a question for Amandine. With the, I didn't quite understand all those clock things. Are you worried about them being used and then the vibrations being a problem?
Well, the usage is a good thing, partially because it's the sense of the object is made by the movement. So when we restore clockwork, especially monumental or part of cathedral and things like that, we do think of do we have the possibility to keep them in movement? So we don't want to necessarily stop the movement, but we have to think what risk we take by doing that, but we want to do that if possible.
Okay, I mean, it is actually very interesting. People talk about this in contemporary art as well, is you're using an object. So when you ask about risk, that's a little bit different than, you know, something that you can't control. So I look at the objects and I think, well, you're probably okay if you do it on special occasions.
Yes.
You know, you show it once a year or something like that, but it's going to happen if you want to use it. There is a science called tribology,
Yes.
which will tell you about the wear and tear, but that's not a vibration thing, that's continual use. So anyway, I found that kind of interesting because it's useful. I have a suggestion for Eva. On your materials testing, I would suggest a much more difficult experiment. You're showing vibration testing. I don't consider that realistic. First of all, the amplitudes are very large. And
it was one video. It is
yeah, just so people don't get scared, that doesn't happen in a painting.
No, it's just an example.
Yeah. But you're also testing crack initiation. But the real problem is people worrying about, I'm glad you used aged paints, but they're worried about, for example, flakes of paint falling off, which is different than forming of craquelure. So what you might want to try, which is a more difficult experiment, is a bending test, where you support both sides of your specimen and somehow simulate a flake painting. So it's going up and down, and then see if the paint falls off.
You can help me in creating those samples.
Yeah, okay.
So
that's what I said.
I think I know that there are other questions on or other worries about what kind of about other damages, but there's always a start and stuff or in research, and this is the most easiest way, but also it's very complicated, even if it looks easy. So yeah, it would be, my idea would also be to create samples which can cause material loss. Yeah. Would be more, what wouldn't be more interesting, but would also be interesting. But yeah, we have to start with something. So if there are ideas, please come and tell me how to do that, or help me.
I also have a question for you. We also tested some vibration on some wood in Henri's lab, and we had some problem with the limit condition when you excitate something for a very long time. You have the boundary conditions. Thank you. So yeah, the boundary condition might change. So what you measure is that the change of the boundary conditions and not the change of the material itself. So maybe, I don't know if you checked that, because I think I saw on your slide that you were hanging the sample.
I was fixing them.
Yeah.
The clamp.
And did you check that this way of handling the sample is like constant in time, like it doesn't?
It looked like, but, so you mean, so the question is, if I checked it, yes, I checked it, it looked very tight, and you said that in your experiments that you overcome some kind of...
Yeah, it was a different experiment, but usually when you start like doing very long vibrational analysis, you just check that.
So, yeah.
So you check that?
Yes, I checked that.
So you're sure that what you're measuring is like a change in the sample and that's the change? Okay, cool.
Yeah, you mean because I saw this, you're referring on this one plot where the amplitude was increasing? Was it that you were referring to?
Yeah, I don't remember exactly the...
Okay.
Yeah.
Yeah, but yeah, this is something very important, of course, to check everything. That's why it's taking so much time to do those experiments, because there are so many... Baustellen and constructions.
I had a question for Amy. First of all, just a compliment on your methodology to measure ambient vibrations for a year and then do testing on equipment and then develop a plan. So that's terrific. The question is on environmental exposure in the building. Will you maintain It must be difficult during such a large construction project. Will you maintain enclosures to keep temperature and humidity constant? This is not vibration, sorry, but
no, but
curious.
You're right, it does kind of all relate to each other. So there's a few points to this. So the first point, which I know people have mentioned already today, in my specific case, we're very lucky that we are very early on in the process of this very complex big project, and that heritage and conservation has a voice. So we are in a very fortunate position to have the time to put together a kind of comprehensive methodology of what we'd like to do over the entire course of the project, and actually have financial buy-in and support, which is very rare across many industries. So that's one very lucky thing, but also we've worked hard over, I think it's taken 4 years for me to get to the point we're at today, where we are about to start. So, you know, not easy. Simultaneously, as we're developing this big vibration survey, we've also been looking at the environment of the entire building. Again, very similar in terms of the fact that it's quite a complex survey to carry out because of so many different locations and factors. So at the moment, we're working with the construction team to plan what do the temporary services to the building look like when they pull the plug and start taking all the wires out and everything. So we've looked at zoning the building and understanding what are the areas where our most vulnerable in situ collections will stay, and what are the environmental parameters that we need to keep in those zones. And we're currently working with that kind of construction design team to understand what temporary services and how we can enclose those parts of the building to attempt to keep some sort of consistent environmental stability. So, yeah, but you're right, they kind of go hand in hand, and these are kind of two strands of big projects we've been doing over the last few years. So, yeah, thanks.
Martine de Palien, Musée du Louvre, département des peintures. It's more a question for Mr. Garcia, because I was happy you mentioned the role of the frame. And in real condition, when we are, for example, in an emergency case, because there are building works in the museum, it's not often possible to monitorize the canvas. So it's more often the frame that it's the sensor put on. I'm looking at Sandy because she knows that. And is there, how is it possible to know is there a gap and a link between the monitorizing the frame and the results on the canvas? And maybe do we know something about the way to frame, the framing plates and something like that? And there's also the hanging system. So there are many details I'm very curious at.
Yeah, thank you. At the moment, in the way that I am doing it, is that obviously I have modeled first the canvas, but I was aware of the frame. And the first approach that I'm taking is considering that the frame is rigidly attached to the wall, you know, with mirror plates. But I'm also incorporating the effect that any buffering system could have, meaning that it will behave like a spring. And I'm also considering when the frame is hanging from chains. So if I model that frame, like in those conditions, with the accelerations that I can measure in the frame itself, I can transform them into the accelerations that is going to be in the points that the canvas is in touch with. So I'm kind of like splitting the problem in 3 sections. The first one is the canvas itself, then knowing how the frame is going to behave and using those values to input in the canvas, and then how the wall is going to behave, inputting those values in the frame and inputting the values of the frame in the canvas. And for the frame, I'm considering basically most used hanging systems, that is the mirror plates. Sometimes they use a buffering material between the mirror plate and the wall, and the hanging from chains and supporting in the lower bit against the wall. So this is my idea. It's still work in progress. At the moment, I'm focused on the most simple case, that is just screwing it with the mirror plates to the wall. Yes, it's work in progress. Did I answer your question?
Yes, I think it's a question we have, of course, for permanent presentation, and also in the case of transport, because there's also the question about the frame and the way the painting is framed, and if it's better to transport without the frame.
Yeah, thank you. Thank you very much.
Il y aurait une autre question ou remarque?
Yeah, I have a remark for François-Xavier Bécaud from Matelis Company. I'm a little bit outside of this community, but I'm very glad that Sandy invited me here. I'm really impressed by the number of data and the methodology for the measurements and the evaluation. I'm very, very impressed, so congrats to all the presenters. I have a question for Eva, because you collected a number of data, which is also very impressive. Did you consider to use machine learning to try to draw some behavior, general behavior, that you could replicate under the measurement and under control tests?
You mean measuring the real moment and then replicate it in the laboratory, for example?
Yeah, the idea of this is to take into account the variability that you obviously have in the real life, and that you cannot reproduce, or at least to some extent, in the measurements. And by using some machine learning, so data mining and data engineering, so generating a lot of data numerically, you can then have a larger view, and not considering a single measurement, but also the variability and dispersion envelope instead of having a single curve.
I didn't. I know that some can think into this direction. I didn't, because it's too complicated for me. But I think the data could give that. But maybe I also didn't understand the question incomplete, because what I can say is that a colleague of mine, he transferred real data. He measured during an art transportation, not in a museum like I did. He measured data out of the acceleration data out of the art transportation and put that into the laboratory, and can now do like those vibration moments or long-term hours in the laboratory. But thinking about the 5 hours or 500 hours I measured, putting that into some bigger machine learning system, I actually right now I don't know how to do that. But maybe there would be the possibility, because the data is there.
Yeah, the idea is to collect, and instead of considering, because I mean each painting is unique, and instead of considering each occurrence as a unique event, then you create some clusters which have similarities to some extent, and then think in terms of a smaller set of data that you could use then and in measurements or numerical simulations that you could replicate, make some variations, and then pair comparisons, but on a limited set of representative data.
Would be interesting, yes. That's a
Thank
good idea.
Very much.
Say one comment. I just wanted to say a comment quickly that I've kind of noticed over the whole day and speaking to some of my colleagues here. This is really interesting because we have professionals coming from a heritage and conservation background, education, and then obviously we have our colleagues and professionals coming more from an engineering and a scientific background. And so I think one of the hardest things that we find is communicating and using the same language and understanding each other, because I think what you've done coming as a conservator and then essentially going into a territory that, I have no idea, I don't come from a science background or an engineering background, to try and run, really scientifically strong tests. That's not something that I would feel comfortable doing. And so I think part of the importance of having a colloquium such as this is just talking more and understanding how to bridge that gap of how we understand each other and working together. So yeah, just thank you.
Il y a encore des questions?
Non, mais c'était une jolie conclusion déjà. Mais la journée a été assez productive, je trouve, très intéressante. Je te laisse conclure.
Toi, bien sûr.
Oui, bien sûr. Bon, bah, thank you for the speakers. Pas beaucoup plus de choses à dire, si ce n'est vous donner rendez-vous demain donc à 9h30 à Aubervilliers, au département des restaurateurs, 124 rue Henri Barbus, pour les ateliers, avec Fifox, l'application installée sur votre smartphone. Vous pouvez d'ores et déjà lire les énoncés de petites expérimentations qui vous sont proposées sur la clé USB. Si vous ne l'avez pas eu, il est encore temps de venir la chercher. Et je crois que c'est tout. Alors, je voudrais quand même remercier l'ensemble des collègues, là, toute l'équipe organisatrice pour cette journée qui, encore une fois, a été fructueuse. Et merci aux intervenants pour tout ce travail. Ah oui, et dernier mot, n'oubliez pas de rendre ce soir, là, vous rendez votre casque et vous récupérez votre pièce d'identité. Si vous avez déjà rendu votre casque et pas récupéré votre pièce, c'est le moment de le faire. Merci.